All right, good afternoon, everyone, or good morning, depending on when you're watching this video. We are going to jump into our final unit of the year. As you know, we've finished differential equations, but we are going to dive into what I call the foundations of mathematics. So many of you indicated earlier in the year that you wanted to take a look at symbolic logic, and that is what we're going to do this week. And later in the quarter, we are going to jump into proofs and other just foundations of why math works. So to start, let's take a look at symbolic logic. So this is section 7.01. Intro to Symbolic Logic. So the first thing that we need to do is take a look at some definitions. So the first one here is a proposition. And you may have heard this word in your English classes, but if you haven't, it's essentially just a sentence that is either true or false. So looking at this, the true or falsehood of a sentence is going to be extremely important for the next couple weeks. So if I say a statement, it has to be either true or false in order to be classified as a proposition. And this is denoted with a lowercase p. So there are going to be two p symbols that we're going to use. One is lowercase and one is capital. The proposition is lowercase. The other one that is uppercase is the predicate. So again, this might be something that you have used in an English class, but in math, it means something specific. So here, this is a sentence whose truth or falsehood depends on a variable. So this is already something that you can see is going to be very mathematical, is that key feature of a variable. Sentence whose truth and falsehood depends on a variable. So these are two things that we are going to take a look at today. And then, of course, if it's a sentence that is neither true nor false, nor can be true or false based on a variable, we just say it's neither. It's neither going to be a proposition or a predicate. So here we have 1, 2, and 3. Sorry, it looks like a B, but that's a 3. So some examples of this here are a few statements that we're going to take a look at. So if I have the statement 3 plus 2 is equal to 5, I want you to think, which category do you think this would fall under? Is it a sentence that is true or false? It is a sentence that the true or falsehood depends on a variable, or do you think it's neither? So take 5 seconds on your own, decide which one do you think it is. Okay, so this one is actually going to be a proposition. And you may have guessed that, but if you didn't, this sentence is true. There is nothing about it that is depending on a variable. It is unambiguously a true statement. On a similar note, we know that this is not true. This is false. So because it's also a false statement, this is still a proposition. So it doesn't matter that it's false. It's still a proposition. It fits our definition, a sentence that is true or false. So it just has to meet one of those criteria. Something that you might look at in terms of a variable is if I have this statement x squared minus 2 is equal to 0. This is clearly, it could be true, it could be false, but it depends on what x is. If I say x is 2, well, then 2 squared minus 2 is not equal to 0, and that would make it a false statement. But it's dependent on what x is. So this is an example of a predicate. And so an example of something that would be neither, it's usually just some statements that might look like questions. So if I say, what time is it? Well, that's not a true or false statement. And if there's really not a variable here that would make this true or false, so this is just neither. It's not going to be a proposition nor a predicate. Now you might be wondering, okay, why do I need to know all of these things? Well, that is going to come into play when we take a look at our symbols that we are going to use for our logic. So let's take a look at what those 6 logical connectives will be. So we have 6 logical connectives. And the first one is going to be meaning not. So we deal with logical connectives only with propositions. So this isn't going to be used for predicates. It's not going to be used for statements that are neither. This will only be propositions, only statements that are either true or false. So I'm going to only use lowercase letters to represent my propositions. So the first one that we're going to use is P. So if I want to say not P, then I use this symbol here. So it's kind of like an L tilted on its side and reflected. So that's a symbol for not. The symbol for and looks like a upside down V. So if I have 2 statements, if I'm saying one statement and another, then I just have P and Q. If you are in my AP Stats class, this looks very similar to a intersection. However, that's an upside down U rather than a V. So it's important to denote the difference between the two. However, they do look similar. So if you are in AP Stats, the or, you might have guessed, is the upside or the regular side V. So P V Q essentially. So this is just P or Q. And then we have exclusive or. So this is, might not make too much sense right now, but when we get into truth tables tomorrow, this is going to be important. Let me make this a little bit clearer. So it's a P and then the or sign with just a bar underneath it. So this just means either P or Q, but not both. And that'll be a little bit more clear when we do the truth tables, but it's just essentially saying that I can't have both. It's either P or Q, not both. The or, on the other hand, it could be both. So if I say I want chocolate or vanilla, then technically I could get chocolate in my dish and I could get vanilla in my dish, and that would fit the or statement. But if I'm saying exclusive or with this symbol here, then that is just chocolate or vanilla, not both. I'm only going to have one flavor in my dish. So that's the difference between the two. The 5th one here, this is if and only if. In math, you might see this as IFF. Once we get into proofs, you'll see that mathematicians are extremely lazy and we like to give abbreviations for everything. So IFF, if and only if, that is known across the mathematical community. And it's just using the sort of double-headed arrow symbol. So if and only if, this just means if one condition happens, only if the other condition happens. So an example that we'll use a lot is an umbrella. So I will use an umbrella if and only if it's raining. So that's pretty much just that statement there. You might also have seen this in geometry as a biconditional statement, where both things have to be true, neither for the whole statement to be true. But again, we'll get into the truth tables tomorrow. And then lastly, we just have if, then. So this is just a P with one arrow pointing to the right. And this just means if P, then Q. If I brush my teeth in the morning, then I'll have good breath. Something like that. Whatever the statement may be. So those are our 6 logical connectives. So we are going to take a look at statements where we would use these in terms of plain English. So I'm going to write out some statements here based on just some things that I know about all of you in this class, just about where you're going to school. So let's take a look at what this may be. So if I have P is the proposition Rachel is going to Brown, and then I have another proposition, so let's let this be Q. Yasmin is going to Northeastern. Sorry, this stylus that I'm using is very touchy. Okay, so then these 2 statements are true. We know that Rachel's going to Brown, Yasmin's going to Northeastern, P and Q are both true. However, we're going to look at 2 statements where these are false. So R is the proposition Alasia is going to Temple. And then the last proposition that we'll use is S. We have Christian is going to UConn. So we know that those last 2 statements, those are not true. Alasia is not going to Temple. Christian is not going to UConn. So those R and S are both false statements. So if I have the statements Q, so let's do examples here, Q and R, then this is just written out as, in plain English, both. So using the and, you essentially have a hidden both in there. So this is going to come in handy when we have parentheses and we need to parenthetize our statements. So here we would say both Q, so both Yasmin is going to Northeastern. And so Q and R, and Alasia is going to Temple. So that would be our statement, Q and R. Both Yasmin is going to Northeastern and Alasia is going to Temple. So here we have a true statement. So we know Q is true. And we have a false statement. So if we have true and false, then this total statement is false. For and, we have to have two true statements in order to have a final true statement. So using that logical connective, we can define what the final truthhood of that whole statement is. So the whole statement Q and R is false because we have true and false is equal to false when we have the and logical connective. When we take a look at another example here with, let's use the if then statement. So if we have not R, so if not R, then S. So if I write this out, I would say if Alasia is not going to temple, then Christian is going to UConn. So as you can see here, so the first half of this is technically a true statement. So we have not false implies false. So you also might hear the if and connector, this connector as implies. So not false, we have true implies false. So our goal here is to figure out the overall truthhood of this statement. If Alasia is not going to temple, then Christian is going to UConn. So you can think about this logically. Again, this is symbolic logic. So logically, if we have the truth statement, so if we make this into if Alasia, well, let's just put in there where she is going, UPenn. So if Alasia is going to UPenn, then Christian is going to UConn. Well, we know Alasia is going to UPenn. So if this whole statement were true, then the second half of this statement would also have to be true, which it's not. It's false. So if we have truth implies false, then the overall truthhood of this statement is false. So the if then statement can be really tricky just because intuitively it might not make complete sense. But the most important thing here is that the only time an if then statement is concluded as false is if we have true implies false. That's the only time. And we will dive deeper into this tomorrow when we take a look at truth tables. But for today, I just want you to get used to using the logical connectives, the 6 symbols, and translating them into plain English and getting used to identifying whether or not statements are propositions, if they're predicates, or neither. So that's what your classwork will be for today. So take a look at Google Classroom, look at the 7.01 Symbolic Logic classwork and exit ticket, and please submit that by 4 o'clock on Tuesday, March 17th. Just take a picture on your notebook and then upload it just like a regular homework assignment. All right, you may log on to my Zoom call at 1 o'clock if you have any questions. If not, you can email me if you can't log on. I'll be available to take questions until 4 or so. So thank you all and have a great rest of your day.